Thank you very much. Thank you, Niloy. And I apologize that I cannot see you in person, but I'm already used to this experience to give talks over Zoom. So I would like to talk today about what we call geometric deep learning. So I will probably half of the talk I will spend about the basic ideas, how we do deep learning, deep neural networks on geometric structures, and then I will talk about some more recent stuff, including papers that we presented at this conference, which is on generating 3D objects, and in particular human bodies, whether it's hands, faces, and so on. So we are in computer vision, so I guess you've seen this slide a zillion of times, so let me remind you just for a very brief instance that deep learning no doubt has had a dramatic impact on computer vision, and it probably was one of the communities that first rejected it and then also pragmatically embraced it, and it has changed it very profoundly. So nowadays we are at an interesting time where deep learning has worked in some applications. In some other applications, it's even not clear how these methods are useful. And in the past couple of years, or slightly more probably, an interesting direction has emerged, basically trying to apply deep neural networks to data that doesn't look like traditional grid structured data, like images or acoustic signals, where these methods have excelled. And these are, for example, graphs like social networks, different biological networks, molecules, and obviously 3D objects, 3D shapes that we deal with in computer graphics, geometry processing, and computer vision as well. So this is what we call geometric deep learning. So the term comes from a paper that I co-authored with Jean Bruna, Jan Lecan, Arthur Schramm, and Pierre van der Geinst, where we somehow, the paper in itself was not really anything new. It's just summarized some dispersed activity in different fields, and basically we thought that it is an interesting field that is emerging, and indeed it has emerged quite dramatically, and I would say more broad topic of deep learning on graphs, what is sometimes called graph representation learning or relational inductive biases, has been extremely broadly adopted in the machine learning community. In fact, it has been this year in ICLEAR, one of the main conferences in machine learning, was one of the prominent topics. And these models have been used everywhere, from recommender systems, social networks, to even particle physics, social science. We sold a company to Twitter that was doing fake news detection using graph neural networks. A lot of promising application in chemistry, pharmaceuticals, and so on. So today I would like to talk about the field of this workshop, and the computer vision audience is obviously interested in vision and graphics applications, and this is also interesting to see how this field has been transformed. So when I started, and unfortunately that's been, thinking of it, it's been quite a while ago, basically people in computer vision were quite skeptical about 3D. So when typically you would tell people in computer vision that you're working on 3D geometry, they would say, oh, you work in computer graphics, because in computer vision there was no 3D. If you look even at acquisition devices, you could easily get a 2D camera that snaps a picture of the world, but something that captures a 3D image at depth was, of course, this technology existed, but it was extremely expensive and extremely big. And 15 years ago, you would buy a 3D sensor for the cost of a car. And this has obviously changed quite dramatically. Kinect was probably the first revolutionary product. I was involved in an Israeli startup called Envision that evolved into RealSense after being acquired by Intel 8 years ago. So now we have 3D sensors on your iPhone. And basically we have an abundance of 3D data. You can also reconstruct 3D data from images. So you have LiDAR scanners on self-driving cars. And actually it's interesting and representative that the nominations for Best Paper Awards, there is a lot of works on geometry. including our own work on hands that I will show towards the end. But you can see, for example, mesh convolution hand reconstruction in the wild, deep geometric functional maps, and so on and so forth. So it's really probably an evidence of how the field has developed. So I like very much this to show this video that is already old, more than 5 years old. And this was a technology that was developed by a Swiss company called FaceShift that was acquired by Apple in 2015, and now this is what powers some of their features that were originally introduced on iPhone 10, the Animoji. Basically, this is markerless motion capture. It allows you to deform in real time an animated character that follows the facial expressions of the actor in front of it. And if we look at the underlying problems, basically there are two problems. One is the problem of correspondence. Basically, we need to find correspondence between the noisy real-time input from the 3D scanner to some canonical body. In this case, I'm showing a body. In their case, it was a face. And then we need to synthesize a new pose or a new view of this body that repeats the input scan. And basically, the way that we propose to address both of these problems, as I will try to convince you in this talk, is using geometric deep learning. Now, when talking about deep learning, right, and talking about geometric information, basically, unlike images where the typical representation for images is a matrix of pixels, right? When it comes to 3D geometric data, there is actually a lot of different choices. So you can think of images as collections of two-dimensional views. You can think of volumetric representations, right? And volumetric representations can also be implicit functions, for example, as you've probably heard in one of the previous talks. Point clouds, for example, are very popular, especially in applications such as self-driving cars. In computer graphics, we like to work with surfaces, basically discrete manifolds, typically represented as meshes. And each of these representations has its own set of methods. So actually, about 5 years ago, many interesting works have emerged about trying to apply deep learning to geometric data. And most of these methods followed the traditional architectures. So you can extend easily convolutional filters to 3 dimensions. Of course, at the expense of computational cost and waste, because most of these objects are actually empty. So basically, you're interested just in the boundary surface. You don't care what's inside. It, of course, depends on the application. Maybe in medical imaging, you actually do care a lot about what happens inside. Also, you don't have any environments. So basically, what we try to advocate, and fortunately, this approach is now quite popular, is to try to work to change the point of view, to work with our 3D objects intrinsically. So you can see in illustration here the difference between intrinsic and extrinsic approach. Instead of applying the filter to Euclidean realization, basically the embedding of the object, we want to consider it as a manifold, as a two-dimensional surface, and apply the filter on the surface itself, doing which endows the neural network architecture automatically with invariance to deformations. So if you want to solve problems like finding correspondence between different poses of the human body, this is very good because you start with something that is already invariant to inelastic deformations, which are a good model or a good approximation for human body poses. And if you think of it also historically in a longer perspective, basically this is the kind of inductive biases that made deep learning successful. Basically, convolutional neural networks excel in assuming shift equivariance that makes a lot of sense in computer vision problems where it doesn't matter where the object, for example, is located in the image, as long as it is the same object. And we try to generalize these concepts to non-Euclidean structured data. So basically, convolutional neural networks were extremely successful for images. We try to emulate similar architectures for meshes. And for this purpose, we need to reproduce the 2 key building blocks of these architectures with small number of parameters, basically number of parameters that is independent on the input size. So we want to do efficient weight sharing, and we want linear complexity in the input size. And the first work where we proposed an architecture that probably by today's standard is quite naive and probably not extremely well performant was what we call geodesic convolutional neural networks. And basically the idea was that we want to generalize the way that filters are applied to non-Euclidean surfaces. The big difference being that the way that the data looks like at each point differs because we don't have any shift in variance. So the way that we extract, for example, something similar to a patch of pixels in an image would be different on a mesh or on a graph. So speaking about convolution, which is the first ingredient of such architectures, we have in the Euclidean setting two ways of defining convolution. One is in the spectral domain, and one is in the spatial domain. And then this comes from properties of the Fourier transform being an operator that diagonalizes the convolution. Convolution can be thought of as a Toplitz's operator. And we can generalize convolution in the frequency domain by basically finding an analogy to the Fourier transform. And a good analogy are eigenfunctions of the Laplacian operator. And if you are not familiar with spectral analysis on meshes, basically you can define a local operator that does some kind of weighted averaging of a function in the neighbors of the vertex. So basically it takes the local average and subtracts it from the value of the function at the vertex itself, giving rise to what is called the Laplacian operator. And basically it is ubiquitous operator in differential geometry. It's called the Laplace-Beltrami operator. And its eigenfunctions form an orthogonal basis that allows to do Fourier analysis on manifolds, or for the sake of this discussion, on any domain. You can actually write Laplacians even on metric spaces, for example. So the simplest approach to defining spectral convolution is just using exactly this analogy. So you do forward Fourier transform by projecting on the Laplacian eigenbasis, multiplying by diagonal matrix of the filter coefficients, which is now expressed in the frequency domain, and these are learned coefficients, and then doing the inverse Fourier transform. The problem with this approach is that it is basis dependent, so the coefficients of this filter will not generalize across domains. And here is an example of a filter that does some kind of edge detection, and if I even slightly deform this object, the resulting filter will, the output of the filter will look completely differently. And the reason is that the underlying surface deforms, the Laplacian changes, the eigenvectors change, so basically it is extremely unstable. So a better approach would be to replace this explicit eigenbasis by a transfer function that is applied to Laplacian operator, in the operator sense that it's applied to these eigenvalues. And if this function can be expressed in simple matrix vector terms, then you can actually bypass the explicit eigendecomposition altogether. Basically, you can express it as powers of the operator. So even though it comes from the spectral domain, it is actually a local spatial operator that you apply on your mesh. Now, polynomial filters were very popular on graphs and are still one of the simplest approaches to do convolutions on graphs. On meshes, this is not the best choice, and actually nobody does really polynomial filters. It is preferred to do rational filters, and the reason is that you want to be independent to the resolution of the mesh. Basically, if you have these two meshes, polynomial filter will have a compact support that depends on the power of the polynomial or the degree of the polynomial that you take. And of course, it will change a lot with the resolution of the mesh. Now, the deficiency of these spectral methods is them being essentially isotropic. And a good example is when you apply such filters on a regular grid, you see kernels with radial symmetry. And the reason is that the Laplacian operator basically averages your neighbors. It is not sensitive to direction. And on graphs, this is necessary evil because you don't have really a canonical way of ordering your neighbors. Basically, any permutation of the neighbors of the vertex is legit, right? So basically, you want some permutation invariant function that aggregates your neighbors. On meshes or on discrete manifolds, we actually have more structure. Indeed, we have some ambiguity. We can choose in an arbitrary way, for example, the first vertex, but once we have chosen it, we can order all the rest of the vertices in, for example, clockwise direction. So we don't have a permutation invariance, we have rotation ambiguity. And this allows us, for example, to do anisotropic filters. So we can define an anisotropic Laplacian. So we can diffuse information not uniformly isotropically in each direction, but we can have some preferred directions on the inflows. So if we look from the operator view, basically, if we have some geometric object that is described by, let's say, positions of the vertices and some triangulation, some mesh, and let's say we have an operator that is defining it, let's say the Laplacian. And basically what we want our neural networks to learn is some kind of features. So depending on the problem, these can be either local features that are defined vertex-wise, or can be global features, some shape descriptor, right? So if we have another another shape that is obtained by remeshing the first one, let's denote it by X wave and T wave, and let's assume that they're related by some functional map. So basically it's a map that transfers functions from one shape to another, and let's assume that it's area preserving. So its representation in the respective Fourier basis will be an orthogonal matrix. Then under these technical, but I would say pretty reasonable assumptions, we can show that remeshing invariance boils down to these functions that such an architecture can learn being functions of the eigenvalues of the operator. So in a sense, it's very disappointing. Basically, it's a very boring thing that you can learn, right? It's basically a one-dimensional spectrum of some operator. So the question is whether we can do something better. And something better can be a learnable operator. And if we look at the recipes for doing non-Euclidean convolutions, basically what I described so far was a linear operation with fixed operator. Basically, we have some features defined node-wise, and I multiply them by some matrix with local connectivity that I call here A. It can be the adjacency matrix, it can be the Laplacian, it can be some power of the Laplacian or combinations of these, but basically the operator is fixed. So the second possibility would be still to have a linear combination, but now the coefficients that we use for linear combination will be feature dependent. So this is the kind of mechanism that is popular in graph neural networks that is called graph attention. And the monet architecture that I will describe in a few minutes also falls under this framework. And finally, we can think of a completely generic nonlinear operator that in graph neural networks is called message passing, and we call edge convolution for meshes in point clouds. So let's talk for a second about this second option of using linear but feature-dependent aggregation. So basically on meshes we can do local charting. So we can represent our mesh in a local system of coordinates. There are many ways of doing it. One of them, for example, using local geodesic polar system of coordinates. So we have radial and angular coordinate. And in this local system of coordinates, we can define a system of weighting functions, which uses a kind of soft pixels. So basically, I will use them as weights to aggregate information from the nodes of the mesh. And this way, you get a fixed representation for each position on the mesh that is independent on how dense the mesh is, what is the connectivity, what is the degree of each vertices, whether the triangles are bad, thin, or so on. Basically, it gives us the analogy of a pitch in an image. And once we extract this pitch, actually the extraction itself can be learnable, so these weights can be made learnable, and the parameters can be made the parameters of the neural network. We can then apply a filter to it. And basically, you can think of all these construction as a Gaussian mixture. And we can, basically this way, we can define local oriented kernels, and the geodesic convolutional neural network that I described before is a particular setting with certain configuration of fixed kernels. And this is how the learnable kernels look like. So I should say that we got quite some mileage with this architecture. It works, still works extremely well in some applications. And we use this, for example, in a collaboration with a very cool group working on protein design from EPFL, from Lausanne, that appeared on the cover of Nature Methods in February this year. Basically, we use this architecture to predict interaction between proteins that we model as surfaces with some features that represent chemical properties such as electrostatic charges. And this was used to design proteins that bind to certain targets. So if you think of this as holy grail of drug design. And we have very promising binders, for example, for PD-L1 protein, which is a complex that is used as a target for cancer immunotherapy. Another curious application domain is particle physics, where monet-like architectures were used to model particle detectors. And I was involved in a collaboration with people from the IceCube neutrino detector. And there are also some efforts at the LHC where they try to use these architectures to better detect interesting particle physics events. So in computer graphics applications, this was a really cool idea to do correspondence. And again, you can think of this as a basic building block of deep neural architecture that can be used for different purposes. So we can do shape correspondence, for example, we can do shape classification, we can do shape descriptors. So these are examples of correspondence. We got very good correspondence, and now obviously there are better results, but that was, I remind you, almost 4 years ago. And one thing that, for example, you can do, you can use this convolutional mesh architecture in combination with, for example, functional maps. So basically, we produce features that are then used to compute a soft correspondence between two shapes. And that was a collaboration with Orly Tani, who is now a postdoc with Leo Gibbs at Stanford. And actually interesting that in this year's CVPR, there was a follow-up work from the group of Max Ovsyannikov on deep geometric functional maps. By the way, also candidate for best paper award that produced significantly better results than we did 3 years ago. So let me briefly describe the last non-linear architecture, and then I talk about synthesis problems. So in the most general case, we produce features by some non-linear function that is applied to local, or actually not necessarily local, values of the function on the mesh. And here is a generic way of writing it. So basically, we have some permutation invariant aggregation operator. Usually, it's a sum or a maximum that basically takes some local neighborhood of a vertex I and passes it through a parametric function that is usually implemented as a small neural network. So basically, we pass pair of node-wise features, xi and xj, and possibly age-wise features. So these, in the simplest case, can be just scalar weights. For example, this can be the cotangent formula that allows you to implement the Laplacian operator. And then we aggregate this with these learnable functions with permutation invariant operator, and we can apply it to point clouds. So that was exactly the work that I did with Justin Solomon and his collaborators from MIT. We applied to point clouds where actually the structure was not represented by a mesh, but as a graph. And the graph was learned on the fly. And you can see that some popular architectures, such as PointNet, is a particular setting of this architecture, and Monet, that I mentioned as well, can be cast as a particular setting. Now, yet another discussion is how to make this into a viable neural network architecture. And we know from computer vision applications that depth makes a lot of sense in images. It is actually, I should say, I have big doubts whether it makes sense in graphs, in general graphs that look like small world social networks. But for geometric graphs, for point clouds, for meshes, deep architectures make a lot of sense. One of the problems is that they're difficult to train. Basically, many times these operators like to smooth the features. They act as low-pass filters. So we need to introduce residual connections. And in this CVPR, again, we presented a paper where we show the principled construction of what we call affine residual connections that allow to train mesh neural networks significantly better. So let me move to the synthesis part, right? I promised you to talk about human bodies. So we talked about the analysis or correspondence problems. Let's now talk about synthesis. Now, I should say that when talking about synthesis, we need to distinguish between two problems. One problem where we synthesize the coordinates of a given mesh, and another problem which is significantly more difficult, where we also synthesize the connectivity. So most of the work that we did in our group assumed that the connectivity is given. And actually the first work, to my knowledge, on intrinsic mesh autoencoders was done by us, again in collaboration with Orly Tani and Amish Makadia from Google back in 2017. And basically what we did here, we tried to solve the problem of shape completion. I would say that in retrospective, probably everything that could be done wrongly in this paper was done wrongly. I don't like the way that we solved this problem, but it was still probably the first intrinsic autoencoder architecture. So basically what we tried to do, we had an encoder and decoder, and we used the decoder, we trained it on collection of shapes with given mesh. So we tried to reconstruct the input by encoding it and decoding it. Then we discarded the encoder and used only the decoder. Basically, we used the latent space to synthesize plausible human shapes, and we synthesized them in a way that they match some noisy or partial input. And it worked reasonably well, at least compared to state of the art that existed at that time. We produced significantly better results. Again, nowadays you can do way better. Here are some examples. So this is the completion of the Faust scans. Basically, these are human shapes. You see that the results are reasonable. The face is a mess. The fingers are also a mess, but we didn't especially model these parts of the human body. And also our meshes had very low resolution for these parts. So now we can do much better, as I will show you in a few minutes. And these are results from Kinect point clouds. So again, plausible, but nothing spectacular by modern standards. And there was a follow-up work actually by my former postdoc, Emanuele Rodola, who is now a professor at La Sapienza in Rome, and my current postdoc, Luca Cosmo. And basically they added a very smart idea. And the idea is the following, that basically they want to preserve some global structure. And this global structure comes in the form of pairwise distances. So basically what they look is at the distances between the vertices of decoded meshes from the latent representation, represented here by Z, and the distances of the linear combination of the latent vectors. And they wanted these to coincide as much as possible. Alpha here is some number between 0 and 1, which is selected randomly, and basically this is done for a collection of shapes, pairwise shapes. So this seems to be a very smart trick that works very well, and they were able to produce significantly better results than what we had. So you can see that here the face looks reasonable, and the fingers look well, and in general the results look much nicer. And here are some examples of randomly sampled meshes from the latent space. So some of them are disastrous, but overall it's not that bad. So it seems to be learning reasonably well the human shapes. So another thing that we did is, it is actually inspired by the work of Isaac Lim, who presented earlier. And they had, at ECCD 2018, they had this idea of local charting on meshes using some ordering that in particular was a spiral ordering. And they applied this idea to shape correspondence using some kind of alignment of these one-dimensional features that are obtained by spiral scan using, for example, LSTM networks. So this is, I think, not the right use of this kind of spiral ordering. And the much cleaner way is to assume that the mesh is fixed. And that's exactly the synthesis problems, where you try to generate the coordinates of a mesh. So you can pre-compute these spirals. They never change because the mesh never changes. So you can you just reorder your neighbors, and that's all. And you keep them only once. And then basically your convolution just becomes simple matrix multiplications. So you can combine it with pooling, you can combine it with mesh coarsening, and that's the kind of architecture that we call spiral net. Basically, we do an encoding that does progressively coarsened mesh with these spiral operations, and then decoding from latent vector, we assume that the connectivity is fixed. So it's some canonical face or canonical body or canonical family. And this seems to work extremely well. So we got state-of-the-art results for shape reconstruction, while also working significantly faster than previous models such as COMA, the work of Michael Black. So less parameters, less time, and more accurate. And it allows to do these kind of models allow to do the standard things that you would do with encoder-decoder architectures. You can do interpolation or extrapolation in the latent space. You can, for example, interpolate or exaggerate facial expressions. You can do arithmetics. You can take a person in one expression, subtract the neutral version of this face, add another identity, and you get the new person with the expression of the first one. And we can also do hybrid architectures where the encoder is not a mesh, but for example, a point cloud encoder. So these are recent results from a PhD student in my group together with Stefanos Leferiot and Mehdi Bari, that basically he has a very cool architecture for that inputs a point cloud and produces a mesh also with visual attention that automatically crops the facial surface, also handles correctly the mouth. And you can see here inputs from different devices, some of them high accuracy scanners, some of them, for example, taken with an iPhone. And you can see that the results are consistently good. You can also have very exotic hybrid architectures. So if you look at this image, it seems that what you see on the right is quite mediocre reconstruction of a 3D face from a 2D image. But don't be misled, what you actually see here is reconstruction of 3D face from the genetic information of the lady on the left. So this is a cool line of work that my collaborator from Belgium, from KUL, Peter Klaes, is doing, and he heads the facial genomics lab there. So this is obviously a little bit wishful thinking to try to completely predict the way that the face looks from DNA, but at least you can predict some features. And they're trying to understand actually what is predictable and to what extent, what properties are, for example, inherited. And basically, we are working together on face models that enable this research. One of the cool applications, of course, that is probably a little bit overselling and compromising to some extent this field is to say that we are able to reconstruct the phenotype from the genotype. Unfortunately, it's significantly more complicated. So let me talk and finish with the last work that we presented at this conference. And this is the work of Dominique Coulon, who is also a PhD student in my group, co-supervised with Stefanos, on mesh convolutional hand reconstruction in the wild. And basically here we are looking at hands. This is extremely important part of our body, especially when it comes to applications in virtual and augmented reality. Basically, these are our device to manipulate objects in the physical and the virtual world. And we want to be able to reconstruct realistic hands from 2D images in the wild. So that's the hybrid architecture that we work with. Basically, we have a traditional CNN that encodes the image into a latent representation, and a mesh decoder that uses spiral convolutions that decodes the shape of the hand. And it works very nice. So we have an earlier version that was presented at BMVC last year. At this year, we are presenting a more sophisticated version of this work in collaboration with a company, Ariel AI, that actually does it on a smartphone faster than real time. And you can see here Dominic presenting this demo on an old version of iPhone. This is working more than 100 frames per second. I don't know if you can see the video well, but it works smoothly. You can see reconstruction of both hands, you can see reconstruction of the body. So the company Ariel is building 3D avatars that can then introduce into your AR or VR applications. So this is 250 frames per second. Here is another example. So these are also some demos of reconstructing 3D avatars, and the hands are reconstructed using the model of Dominic. So it can handle multiple people, complicated scenes, completely in the wild. So this is an example of an ego view, so something that you would see in, for example, a virtual reality gaming application. So you can see that the hand is present in the scene, and you can manipulate virtual objects in this way. And this is only single frame, so there is no tracking. Basically, this will be next, how to incorporate dynamics of the hands. And basically, there is also a data set that accompanies this publication, which can be used. We got obviously state-of-the-art results that exceeded by far of what currently exists, probably not for long. So let me wrap up and conclude. So if we talk about shape representation, so taking a step back, basically we started with different ways of thinking of 3D geometric objects. We can think of them as volumes, and in this case, actually, we don't have any ambiguity. Basically, we can stick to a fixed Cartesian system of coordinates, and basically, we can apply standard convolutional filters. The price that we pay is high computational complexity, wasteful representation, and also any lack of invariance. Even if I rotate the object, the result, basically the output of the convolutional neural network will change. On the other extremity, we have point-based representations, point clouds, where actually we have an extreme version of ambiguity. Basically, every function that we learn must be invariant to global permutation of the points. So this is the point net kind of architectures that apply shared function to each and every point in the point cloud. So in the middle, we have graph-based representations, where basically we represent a point cloud as some k-near stable graph, and graph neural network architectures are have ambiguity of local permutations, basically how we order the neighbors of a vertex, and slightly more structured are meshes, where we have rotation ambiguities. So I hope that I was convincing enough to say that it is possible to do deep learning architectures on meshes. It is actually good to work with meshes. I think nowadays computer vision domain is not scared of working with meshes. A lot of applications and a lot of works work with meshes. It was not the case even a decade ago. It was considered to be the kind of stuff that you do in computer graphics and geometry processing, but fortunately not anymore. So some of the messages, basically it's geometric deep learning is natural and principled way of learning on non-Euclidean domains, in particular manifolds and graphs. You can think of it as a kind of local learnable operator that is similar to convolutions, obviously weaker because we have less structure. There is a plethora of applications, not only in vision and graphics, but way beyond, and I mentioned some of them. Basically, deep learning on graphs is extremely promising and fruitful field because graphs can be used to model any system of relations and interactions, from biology to physics to drug design to social science to economics, you name it. Graphs are completely ubiquitous. And these methods produce state-of-the-art result. I should say that there has not been such a dramatic revolution as it happened with the introduction of CNNs in computer vision. So it's more like an evolution. So graph neural networks have become a standard technique in machine learning arsenal, but it's not some dramatic change that they have brought. And there are several reasons. I actually wrote recently a blog post about it, what I believe would be the next steps to progress the field. There are interesting open problems. So generative models for arbitrary meshes that generate the connectivity are difficult, and there are only few works that try to do it. Incorporating global structure, basically all these methods work only locally, but we know that with geometric structures such as meshes, we have a lot of global structures like topology, for example. Can we impose that the meshes that we generate with such networks, for example, have genus 0? They look like a sphere. And actually, computational topology, basically different topological losses can now be made differentiable and can be incorporated into deep learning architectures. So topological data analysis in general that has been around for at least 20 years, now in the context of deep learning becomes interesting, and there is a renewed interest in this field. So I think it might be also very cool to try to combine these methods in applications in computer vision and graphics. I think there was a work from computational topologists. I think it was Primor Skraba who tried to do it recently, but I'm not sure. Maybe I'm confusing. And it's also interesting that we have very nice theory, differential geometry, that has some theoretical guarantees and beautiful, nice math. But deep learning, on the other hand, is mostly engineering, crafty field. So somehow bridging this gap between things that are a little bit dirty but work in practice, and things that are beautiful in theory, but you need to compromise when you get to the actual implementation. Basically, doing things right and beautifully and correctly, but still making them work, is probably still not there. I think there are many corners cut and many things rounded up to make these architectures work. So I think the last word has not been spoken in this domain as well. So at this point, I would like to credit many of my collaborators on these and other projects. And thank you very much for your attention. If you have time, I will be glad to answer questions.